Dr. Bryan Ormond. He's the director of the Millikan Textile Protection and Comfort Center at NC State University and holds the rank of associate professor in the Wilson College of Textiles. His group developed test methods, standards, protective equipment for first responders and military personnel, with recent work focusing on reducing firefighters' exposures to toxic chemicals, developing and evaluating non-PFAS protective gear, and improving respiratory protection for wildland firefighters. Dr. Ormond's contribution to education and research had garnered recognition by the Fire Service Academia and industry, and being named an NC State Alumni Distinguished Undergraduate Professor. The recipient for the 2025 Dr. John Granite Award for Excellence in Fire Leadership and Management Research, and the ASTM International Professor of the Year for 2025. Dr. Bryan, the floor is yours.
Alrighty. Cool. Thank you for the invitation to be here. I'm happy to come over and spend some time with you and talk today. It's really interesting just sitting and listening to everyone this morning. I was picking up things that I was already planning on saying, and so you'll hear some things echoed throughout what you heard earlier. But we talk about the as Gavin mentioned, the hierarchy of controls and things like that, and we mentioned about the data that's needed, and so what I hope to do is tell you, how do we collect some of that data? How do we develop the test methods to then develop those innovative ideas for the PPE? And so in the lab that in the center that I'm director of now, we really try focusing on the system, not just the material testing, but the system as you wear it. Both in the lab testing as well as getting into the field. And so, you can see this is actually right across the street from my house back last year. And this townhome caught on fire. And so being able to, I just kind of walked out and just watched as the first live actual emergency response I had been to a lot of training facilities, but to sit and watch the firefighters in their element do what they're doing. And they were asking me if I needed any samples for any research, and I was like, no, I'm not going to collect those now. And so we're always trying to start with I'd say the consistent, controllable, laboratory, repeatable test. And it may not be as realistic, and that's always a balance that we fight. Is how do we make it more realistic? Because we can come up with a test or come up with something that works in practice or in principle, but how does it actually work when you're using it in the field in your conditions? And so that's where we always try to push to the field. See if I can, there we go. So as we look at PPE, and the study of PPE really is a study of trade-offs. It's what do you have to give up to get something else, whether that's thermal protection and thermal comfort. And now we're looking at, balancing those two in addition to chemical exposures. And so the academic in me always wants to start from the beginning, the fundamental piece. And so as we try to figure out how do we combat cancer in the fire service, I start looking at, let's go back to the beginning. We have to understand the fires, understand the fire scene. They're all different, whether it's a structure fire, a dumpster fire, a car, electric vehicle, all different types of products of combustion, different routes of exposure that we have to look at. So how do we address those? One of the things that I've sat in a lot of conferences, a lot of meetings where we're talking about different ways of detecting cancer earlier, how to screen for it, how to treat it, all these different types of things, all great work. But it just occurred to me that we were just accepting the fact that they're going to be exposed. And so when I look at it from the design part of the PPE, how do we turn that exposure off? And the PPE can help do that. So can we develop it? One case I'll talk about is respiratory protection for wildland firefighters. So we'll go through a little bit of that. Looking at vapor and particulate protection in gear. This is something that's been picking up considerably recently. I won't go into this today, but we have a whole quite a few years, I guess, worth of work, looking at manufacturing gear, looking at performance without PFAS chemistry. So if you're interested in that area, I'll be here through tomorrow. So I can definitely talk your ear off about what happens when we transition to non-fluorinated chemistries. But then, as was mentioned before, it's not just the gear. If you have gear that stops these things, now it's on the gear. How do you decontaminate it? How do you decontaminate yourself? And one of the things that I always leave and talk to the firefighters about is you don't have to be perfect. We always talk about what's the most effective thing we can do. Well, the most effective thing is the thing you're going to do consistently every day. And so I look at it as not focusing on elimination of these hazards, because we're never going to eliminate every hazard you're going to face. It's about mitigating them every single day. And so if you're coming in and you're doing the thing that reduces exposure by 2%, 5%, 1%, those all add up over that career. And I think that's a lot easier for departments to implement because you don't have to do everything right every single time. You have to continue to show up and continue to do it. And so as Gavin started, it sort of mirrors this as well, looking at respiratory protection first, and then the dermal or skin exposure. When we look at respiratory protection, specifically, when I look at it in terms of the U.S. Fire Service, we have wildland firefighters and structural firefighters, just two different types, very different exposures, very different gear that we look at. And wildland firefighters have no respiratory protection requirement. There is no product for them that is made for them that fits what they need. And so we started looking at that. How do we do laboratory testing to inform what they could actually wear? And so hopefully these videos will work for us here. There we go. So we have animatronic head forms. We can start with the material level test, but you don't wear a flat piece of material. And so we want to go to something like this that is going to be controllable. We can control the breathing rates. We can control how it moves. We have two of these head forms. One is actual full torso as well. And so we actually started working on this during COVID, looking at face coverings, looking at barrier face coverings, respirators, seeing what was effective, knowing that we could help out as little or as much as we can during the pandemic. But then this is always going to go somewhere else, and where it went was wildland firefighting. And so there's this lack of available materials or available products that meet performance requirements. There is a standard. There's an NFPA 1984 standard for wildland respiratory protection. Nothing has ever been submitted for certification in its decade plus years of being there. And so the reason for that really is a lack of perception of a market. Are people actually going to use it? Are you going to make something that they're going to actually adopt? And that accessibility or acceptability is really, really important. Because as I said before, we can make something that is the most protective, technically passes every requirement that we want. But if we don't consider the human element, the human factor, it doesn't make a difference if they don't wear it. And so just like I was saying, the thing that's most effective is what you are going to consistently do. The best piece of equipment sometimes is the one that you're going to wear consistently. And so when we look at this, we're trying to answer questions of not just looking at filtration on the material, but also that fit to the face. And so here's a number of products that we've looked at. We have about 27 different things that we've gone through on our headform system that we've developed. Everything from on this side, you have your powered air purifying respirators, your APRs. Those are going to be the 100 or 50, 25 protection factors. As Gavin mentioned earlier, SCBA being 10,000. And so there's different levels there. And then we go down to the filtering face piece respirators, and then the non-traditional products, the textile-based things, the neck gaiters, the bandanas, barrier face coverings, all these different types of products that many of these are targeted to wildland firefighters. None are certified for that purpose. And so we wanted to see what data can we get? How realistic can we get here? And so when you look at this, just to orient you, the y-axis there is looking at the filtration, looking not just through the material, but what comes around leakages around the face as well. So we call that total filtration efficiency or total filtration efficacy. And on the horizontal axis here, we're looking at inhalation resistance. That brings the human element into it. How hard is it going to be to breathe, right? If something is too hard to breathe through, people aren't going to wear it. And so what we're trying to do is optimize, and you see this area we have highlighted here, above 50% filtration efficiency and below that kind of 250 Pascal breathing resistance. You want to be as close to that top corner as you can to have something that's going to actually work protection wise, but also be easy to breathe through. And you can see there's many of the different traditional respiratory devices are there. But we also start to see some of the different non-traditional, some of the neck gaiters or the barrier face coverings. There are other things that can get you somewhere, maybe not 100%, maybe not that 95% that we look at for true defined respiratory protection. But the problem with wildland firefighting is in the absence of perfection, we have nothing. And so that's one of the things we've been trying to fight in the standard side of things is we're not coming down from 95 or 100 for wildland firefighters. We're coming up from 0. A bandana is not good enough. And you can see where all the bandanas sit down there at the bottom. And so we also want to move to the field and try to look at this on a realistic exposure, smoke, particulates. And so we actually have a small scale live burn apparatus. We work with a local firefighter who built this on his own and brought it to us. And he can burn any number of things in there. We're actually burning more of a wildland fuel package. We also do electric vehicle battery fires and structural fuel packages as well. We were trying to see, we can see things in the lab in a controlled scenario, but what does it actually look like when you have the same chemicals that are actually from the fire, looking at the particulates that are being generated. So we actually ran this for 100 minutes. 1 liter a minute air sampling inside the masks or inside the head forms. And so these are our particle impactors that used to be white. And so you can see the first 2 columns there are just the backgrounds. We had those open to the environment. You can see how much they're just picking up just in that time running. The third column is a filtering face piece N95 respirator. You can see there's a lot of variability. This was the first time we did this, so we weren't sure what we were going to get. That variability is associated with the fit to the face. If it doesn't fit well, it's not going to filter. And you go to the barrier face coverings, you got a little bit somewhat similar, some variability, but then you look at the bandana and it almost looks identical to the completely unprotected. And so there are different ways of being able to show how effective things are. It's not always a number, sometimes it's a picture like this. But as I said before, we can have that product that technically works. Maybe it filters perfectly, but if people aren't going to wear it, it's not going to help. And so we always go to the human factor, the human element. And so we do the physiological testing. We actually did this past year ago this month, where we had firefighters come out, put on the different products. We down selected to about 12 from that 27 that we looked at, had them go through. They did a 1 mile hike up and down hills, things like that, carrying tools. Then they dug line for about 15 minutes, and they walked back. And then they did rolled and unrolled hoses. And the whole time we're measuring core temperature, skin temperature, respiration rate, all these different things to try to understand how much of an impact is this having on them. Because when we think about wildland firefighting, their workload is very different. It's a long period of time. And so how are we going to have something that they're going to be able to wear? Because a lot of times they're not going to want to carry something that's like one of the Pappers with a giant filter on the side, because they just can't. They are limited to what they can carry. And so we're trying to find something that is very lightweight, but also works, but also is breathable. And so a lot of these things came out in our focus group discussions after the fact, when they were talking about, the things that they liked, the things that they didn't. And it was very evident how difficult it is to make a product specifically for them. But the one thing that I always remember from those conversations was that they said very specifically, none of these things were made for us. And I was like, absolutely. They're being forced into this application. They were never made for a wildland firefighting application. And so what we're doing now is hopefully moving forward to take all of what we've learned and then put it in and make something not just for the firefighters, but with them, actually develop it with them. Moving to more of the dermal skin protection and designing PPE to handle that, there are many different ways that we can look at system level testing. And so not just chemical, but we have our PyroMan fire test system. We have our thermal sweating mannequins where we balance that thermal protection and thermal comfort. So we have a number of those in our facilities. You can control environmental conditions in the lab. You can do these on a material level scale as well, right? That's typically what's the certification one. And then we can move to this for more information. But when we think about the other chemical hazards, the liquids, the aerosols, the particulates, gases, vapors, we have system level versions of those tests as well. So whether that's the shower test or liquid tight integrity test, The two that I'll talk about today further are the aerosol particulate and the vapor gas managed simulant test. All three of these are at different facilities right near our campus in North Carolina. So the liquid tight integrity test is over at UL's facilities, where they do the certification testing. The only place that I know of in the world that does the aerosol system test is at RTI International, and then we have the managed simulant vapor testing. And so let's just talk about the issue of what was mentioned before. We focus on the visible hazards. The visible hazards being the smoke, the soot. You can see those on the skin. It was very easy to get people to pay attention to them. This is a way of doing that. You take a subject and you put them in an environmental wind tunnel, and there's a fluorescent tagged particle. And that particle, they blow it around in the wind tunnel. You do these exercises. You can see we have two different loadings, concentrations in the room here. And what you get are images like this. Now you can do it on the full person. We actually did it on the head forms here when we were looking at particulate blocking hoods, right? And so here's a particulate blocking hood in the bottom right corner showing how effective it is. A lot of this is just visual. You can get quantitative data off of this as well. But when we move up to the traditional 2-layer knit hood, you see about an order of magnitude decrease in protection. One thing you don't normally see is the top picture, which is no protection. Normally they don't actually do that with the human subjects. And so you can see even a 2-layer knit hood, as was mentioned earlier, can provide significant protection if it's worn appropriately. We also tested this with the donning and doffing method as well. And you could see these fluorescent particles. You have this really decent protection here. And when you pull it down around the neck and just pull it over, it smeared all of that fluorescent across the face. These are, again, looking at the visible hazards. When you look at the other way of doing this, they have a slightly different version they've developed, and you can see a standard turnout. So the standard turnout here, we didn't have a SCBA on, so there was nothing around the waist. This was actually for a fire investigator type exposure. And you can see where all that's sliding up. Everything, we think about protection, the materials that provide protection. You have a barrier in this. It's not going through the barrier. Things that are getting to the skin in a turnout are coming around the interfaces. They're coming in the jacket collar, up the waist interface. And you can see that happening here. We've done a lot of other testing on different types of ensembles, from base layers all the way to the structural suits. And you can look and see all of those different areas where things deposit on the skin. Now, switching a little to the invisible part, right? The hazards that you can't see. Looking at the vapors, I don't think anyone expects a structural suit to be vapor tight. You probably wouldn't want it to be vapor tight because then you're dealing with a lot of heat strain. But what we have the capacity to do, we have the only managed simulant test or MIST facility at an academic institution, probably in the Eastern or in the Western Hemisphere. There's a couple at test labs, a couple at military bases, but we actually have it. It's been there as part of my PhD research back in 2008 was when it was built. And so we have the opportunity to understand that test. It's mainly meant for chem bioprotective clothing, for hazmat suits. We do hazmat suit certification there. I started asking a question, well, why can't we use this for structural suits, right? And so that's what we did. So like I said, we had a FEMA federally funded project looking at fire investigator gear. So we went everything from a base layer to disposable coveralls, reusable coveralls like tech rescue or wildland garments. This one here is actually a particulate blocking prototype. So we put same pattern, but we actually filled that in with a membrane to provide a particulate blocking layer. And then on the bottom, you see the structural suits. So we have a standard structural suit. We have a particulate blocking turnout ensemble as well. And the third one there is basically getting rid of the waist interface. It's a one-piece coverall, trying to see, is that a way to reduce exposure around the waist? As we saw, things come in there. And then from my background, looking at chem biosuits, I went and found a carbon sorptive flight suit at an Army surplus store online, bought every one of them. So we could do testing, because I knew that's a way to stop some of these vapors that we see, the benzene, the toluene, the naphthalene, those types of things that come off of every fire. And so let's look at the data real quick. So when we look at this, if you look on the bottom layer first, the base layer, we're getting a protection factor of around 2. That's what you would normally expect for a just regular shirt and pants, long sleeve shirt and pants. And this is all dermal. Everybody had respiratory protection on, so we're not looking at inhalation or anything like that. When you go up to the disposable coveralls, those are impermeable materials, so you get a little bit of a bump. Now, just to remind you, the SCBA was a protection factor around 10,000. These are 2, 3. Our garments are much less protective. When you go to the reusable coverall, the reusable two-piece, the particulate blocking two-piece, there's not a lot of differentiation there. I can actually explain, some of the differences there. But I want you to look at that yellow bar, the structural suit. Our structural turnout ensembles only give a protection factor of around 10, 8 to 10. So order of magnitude decrease from what's outside to inside. That's a really small number when we consider, hazmat suits. Even the lowest level of chem bio suit is going to be in the hundreds, 70s to 100, something like that. If you go from the yellow bar to the red one, we're looking at the particulate blocking suit. The particulate blocking, meaning it was intended only to block particles, but we can see it's twice as vapor protective because it's shutting down the interfaces. It has things in the interfaces around the waist, in the wristlets, and in the calves, ankle portion, that actually shut down the air transfer, which also makes it hotter to wear. So that's a trade-off that we have to consider. One thing to point out, that top one, we would expect to do better. Right? You would expect a carbon-based sorptive chem bio suit, flight suit, to do better than the turnout. 8 to 10 is pretty much the same thing. The problem with that, it was a coverall. The head and neck were completely exposed. And so here's another way of looking at this data. And you can see we get a ton. These are all averages of 4 subjects each. There's 54 samplers for every person. So we get a ton of data. And so if you look at this, top to bottom is the top of the head to the bottom of the feet. The longer that bar goes out, the more mass of our stimulant that we use was picked up. And we use methyl salicylates, the oil of wintergreen's, a stimulant for mustard gas that was developed by the U.S. Army in the early 1990s when they developed this test. But you can kind of start to see some of the differences. And what I want to point out to you is when you look at the yellow, the standard structural, then you move to the particulate blocking, you can see those decrease. We can actually see that the particulate blocking hoods are also providing vapor protection to the head and neck region, which is why many firefighters report that their hair doesn't smell nearly as much as smoke when they wear these types of hoods. But then you look at this one here and you can see why the protection factor was not great when we summed it up over the total body. You have almost nothing across the body. It's all in the head and neck region. As we mentioned, very thin skin, and as that is taken into account in our body region hazard analysis, where everything is weighted, it significantly drops the overall protection. So that's the lab. How does it work in the field? When we look at this, we wanted to ask that question again because we don't know how well this replicates what you see on a fire scene. It was intended for hazmat chem bio protection. And so we had some changes that we had to make. We went out to a local training facility. And again, this was all about fire investigator exposure. So we did it post-fire. We did 2 different days. One was immediately, I'll say 2 hours after the fire was put out. And the next one was 24 hours after. We had to come up with different ways of measuring because the small samplers that we use in the lab are not good for collecting the Fireground contaminants. And so what you can see, these little colored areas, we've developed silicone samplers to be able to collect the PAHs, the VOCs, things of that nature. And so we're actually putting 3 per location. And there were 10 of those on the outside of every suit. There were 5 on the inside of every suit, or 5 on the inside, 5 on the outside, 10 on the inside, so that we can get that measure of protection factor. What was on the outside versus what was on the inside. We were also, as you can tell, we have some active sampling pumps looking at particulates being picked up, looking at vapors. And so we had these people go in. Our normal test is only 30 minutes in the lab. This was a 2-hour exposure. So you start to add all these things up and we don't know, at the time, don't know how well it's going to relate. How well is it going to predict? Because the whole point here is if we can show that the laboratory testing is a good approximation of the field testing, I can do a lot more lab testing on prototypes, things that are not certified, things that you would never put in live fire compared to going out and actually having to set up and burn structures. And that also reduces that exposure to our potential test subjects as well. And so what we've looked at so far, when we start to compare the results, we narrowed down to these 6 garments. So we weren't able to do all the garments I showed earlier. But if we start talking about the PAHs specifically, so you can see there naphthalene through anthracene were the ones that we really detected. We didn't really get a lot on the silicone samplers of the larger molecular weight compounds. But when we start looking at those and we sum those up, if you look at the two bars at the bottom, the base layer is almost identical measurements, 1.8, 1.9. So that checks out. We look at the disposable coverall. We got 2.9, 3.7. So a little bit of variability, but still same order of magnitude. The next two, similar. We get up here and we have 8.4 and 7.9 for the structural ensembles. So that's a really good. We saw the jump that we expected. And then we got roughly the same thing for the structural suit, or for the chemical protective flight suit. And so what this tells me is this opens a door for us to, like I said, we can start doing that other type of testing in the lab. We're not done with this. Like I said, we have more data to analyze from this, but we also are taking biological samples, and we're getting to those. And we have a follow-on project, not looking at fire investigator ensembles or fire investigator scenes, but structural. Can we go into the actual structure fire and measure these the same way using the same silicone samplers and compare back to the lab testing that we've already done? And so we're working on that now. We'll be running the in the lab portion just when I get back before June 15th. We have about 5 days of testing we have to do. And then we're planning the next phase is to plan all of the lab testing. And so what we're really showing here is just the idea that we can take, there's so much data that you can collect on these different ensembles, the different measurements, the different ways of doing testing, system level testing, whether it's for thermal protection, flash fire, the sweating mannequins for the total heat loss, or what I've shown you here with the exposure piece. Is it's so important to look at the garment as a whole system with what you're going to wear, the helmet, the mask, the boots, everything included, because it's going to give you much more realistic data compared to what you're actually doing and how you are wearing that garment. And so just to finish up here, we have a lot of labs and funding sources that we work with, and FEMA, as anyone that's got FEMA funding will tell you, is one of the most important that we deal with in the U.S. But we have a lot of other groups that we work with, both state funding as well as federal. And then our lab, so I didn't really mention too much about the TPAC Center that I'm the director of, but it's a nonprofit center, 32 years in existence in the university. And our primary function is a testing service lab for industry, for military, for fire service, all those different types of things. And then we tack the research onto that. We got a lot of other people that help to make this happen and get us through all the data analysis, the chemical analysis. There's a lot that goes into those. And so with that, I just want to point out, we do have, if you're interested, that QR code will take you to our website. We've been trying to update it consistently, but we have a number of publications that have come out more recently. And we have some partner groups that we work with at Duke University as well. We have two manuscripts that just came out looking at not air quality, but air sampling in fire stations, seeing when you take that stuff back to the station, what type of exposure could there be, in addition to looking at the new moisture barriers that are coming out on the market in the U.S., the non-PFAS ones. There's brominated flame retardants we have to worry about now that we're seeing. So there's a lot of, every time we think we have one thing sort of solved, there's another one that comes up that we have to look at. So with that, I want to hopefully finish up and be happy to talk during the panel session.
Thank you, Bryan.